Hi everyone, this is Professor M Does Science, and today I want to discuss how to write the Hamiltonian in terms of quantum field operators, and this is another one of our videos on rigorous quantum mechanics. The Hamiltonian operator, which is the operator associated with the total energy of the system, is the key operator in quantum mechanics. One key reason for this is that the Hamiltonian is the operator that drives the time dependence of quantum systems. The basic building blocks of quantum field theory are the quantum field operators that tell us about particle creation and particle annihilation. So you can imagine we'll want to write the Hamiltonian in terms of these quantum field operators. And this is exactly what we'll do in this video. Let's go! We start by writing the general form of a Hamiltonian for a system of n identical particles. For many quantum systems, the Hamiltonian has three terms. First, we have a kinetic energy term, which we call T. Second, we have an external potential term, which we call V. And third, we have a pairwise interaction term between the particles in our system, which we call W. The kinetic energy term T is a one-body operator, which we can write in the usual form, and the associated single particle operators are given by the usual expression for kinetic energy, where this here is the momentum operator. The external potential term V is also a one-body operator, and we can also write it down in the usual form. And in this case, the associated single particle operators V are in general functions of the position operator. These external potential could, for example, be an externally applied field. The pairwise interaction term W is a two-body operator, and we can write it down in the usual form. And the associated two-particle operators W are in general functions of the position operators of the two particles. The most common type of pairwise potential is the Coulomb interaction between charged particles, for example between electrons. But there are also other possibilities, for example the Yukawa potential, first introduced to describe the interaction between protons and neutrons in the atomic nucleus. We have a companion video linked in the description in which we write this Hamiltonian in second quantized form. In that video, we use an arbitrary basis U and just explore the general features of the second quantized form of the Hamiltonian. In this video, we'll do something similar, but instead of working with an arbitrary basis, we'll work with a very specific basis, the so-called position representation spanned by the position eigenstates. This is motivated by the fact that both external potential here and pairwise interaction potential here and here typically depend on the position of the particles. As the creation and annihilation operators in the position representation are what we call quantum field operators, in this video we'll write this Hamiltonian in terms of quantum field operators. We're going to work in the position representation. Starting with one-body operators, remember from the corresponding videos that we can write a general one-body operator F as a symmetric sum over single particle operators. In terms of field operators, these single particle operators involve the integrals over R1 and R2, the matrix elements in the position basis, and then the creation field operator and the annihilation field operator. In our case, we have two one-body operators. The first is the kinetic energy, which we explicitly write as a symmetric sum over single particle kinetic energy operators. And in second quantization, the kinetic energy is given by the integrals over R1 and R2 of the corresponding matrix elements times the creation field operator at R1 and the annihilation field operator at R2. The second one-body operator we have is the external potential, which we explicitly write as a symmetric sum over single particle potential energy operators. In second quantization, the external potential is given by the integrals over R1 and R2 of the corresponding matrix elements times the creation field operator at R1 and the annihilation field operator at R2. All we need to do now is to evaluate these matrix elements for the single particle kinetic energy operator here and for the single particle external potential here. So let's do this. Let's start with the kinetic energy matrix elements. And it will turn out that these are actually the hardest to evaluate. First, let's write out the kinetic energy explicitly as the momentum operator squared over 2m. Next, let's take the constant 1 over 2m outside to end up with this. To make progress, let's quickly discuss the momentum operator p and its associated eigenvalue equation. As the momentum operator is a Hermitian operator, its eigenstates span a complete basis of our state space, and we can therefore write the resolution of the identity in the momentum basis like this. Inserting an identity operator up here, we can rewrite our matrix element like this, where I'm writing the identity in the momentum basis. Rearranging terms, we can rewrite our matrix element like this. And feel free to pause here to double check this step, but all we've done is to rearrange some terms. Moving on, we can now use the fact that these are the momentum eigenstates to rewrite this term as equal to the momentum eigenvalues squared times the momentum eigenstates. This allows us to rewrite the matrix element like this. Let's make some room, and let's write down our latest expression for the matrix element. In the video on wave functions, linked in the description, we evaluate this bracket here between position and momentum eigenstates, and copying it down, we find in that video that it takes this form. Similarly, this other bracket, which we again copy down, takes this form, which is simply the complex conjugate of the first bracket. Collecting our results, we can rewrite our matrix element like this. At this point, it's useful to make a change of variables from p to k, related by the constant h bar. This also implies that dp is equal to h bar cubed dk, and with these new variables, our matrix element takes this form. Feel free to pause here for a moment to convince yourself of this change of variables. To make progress, we need a standard result associated with the Dirac delta function. Specifically, the Laplacian of the Dirac delta function can be written in terms of this integral. Now, this is a general property of the Dirac delta function that we won't derive here, but you should be able to find it in most maths textbooks. Moving on, we'll use this identity to rewrite our integral here in terms of the Laplacian of the Dirac delta function like this. And we end up with this expression for the matrix element. Great! After quite a few steps, we finally have a relatively simple expression for our matrix element, so we'll now be able to go back to our full expression for the kinetic energy. Let's write down the kinetic energy operator in terms of field operators. We have now established that the matrix element appearing in the operator is given by minus h bar squared over 2m times the Laplacian of this Dirac delta function. Inserting this matrix element into the kinetic energy operator, we end up with this very long expression. We now need another general relationship involving the Dirac delta function. Specifically, the integral over R of the Laplacian of a Dirac delta function times an arbitrary function f is equal to the Laplacian of the function f evaluated at the point at which the argument of the Dirac delta function vanishes. Using this general expression, we can evaluate the R2 integral here, and this delta function means that all R2 arguments will become R1, and doing this, the kinetic energy operator reduces to minus h bar squared over 2m times the integral over R1 of the creation field operator at R1 and the Laplacian of the annihilation field operator at R1. And that's it. This is our expression for the kinetic energy operator in terms of field operators. As a quick note, we can use integration by parts to rewrite this operator in a more symmetrical form, where we have this prefactor, and then the integral over R1 of the gradient of the creation field operator, and the gradient of the annihilation field operator. I won't derive this final expression, but it literally amounts to using the standard formula for integration by parts, so it could be a good exercise for you. Going back to our slide on one-body operators, we have now calculated this matrix element for the single particle kinetic energy. And using it, we can add the final expression we have for the kinetic energy operator. We can see that we no longer have two integrals over R1 and R2, but instead we only have one integral over R1. So the kinetic energy in terms of field operators is somewhat simpler than the general expression for a one-body operator. We're next going to evaluate the external potential matrix element here, and the derivation is actually much simpler. Let's write the external potential energy matrix elements. And let's also remember that the external potential is in general a function of position. The key to evaluate these matrix elements is to note that they are matrix elements in the position representation. Acting with the position operator on a position eigenstate gives a position eigenvalue times the associated eigenstates. From the video on functions of operators, we know that the action of a function f of the operator r on a position eigenstate is just the function evaluated at the eigenvalue times the eigenstate. Using this result, we can rewrite this term as v of R2 times the ket R2. And we end up with this expression. This is now just a scalar, so we can move it outside, and we get this. For this bracket here, we can use the fact that the basis is orthonormal, and we end up with v of R2 times the Dirac delta function of R1 minus R2. Let's now write down the full external potential operator in terms of field operators. Inserting this matrix element we've just calculated into our expression for the operator, we end up with this very long expression. We can now evaluate the integral over R2, and this delta function means that all R2 arguments will become R1. So we end up with an integral over R1 of v of R1 times the creation operator at R1 and the annihilation operator at R1. And this is our external potential in terms of field operators. Going back to our slide on one-body operators, We have now calculated this matrix element for the single particle external potential, and we can add the final expression we have for this external potential operator. We can see that we no longer have two integrals over R1 and R2, but instead we only have one integral over R1. So the external potential energy in terms of field operators is again somewhat simpler than the general expression for a one-body operator. Let's now move to the two-body interaction operator here. Remember from the corresponding videos that we can write a general two-body operator G as a symmetric sum over two particle operators. In terms of field operators, these two particle operators take this very long form involving four integrals over the matrix elements and the product of two creation operators and two annihilation operators. In our case, the interaction energy operator W is a two-body operator. And in terms of field operators, it takes this form with four integrals over the relevant matrix elements, and then the product of two creation field operators and two annihilation field operators. All we need to do now is to evaluate these matrix elements for the two-particle interaction energy operator, so let's do this. Let's write the interaction potential energy matrix elements. And let's also remember that the interaction potential is in general a function of the position of the two interacting particles. Just like in the case of the one particle external potential, the key to evaluate these matrix elements is to note that they are the matrix elements in the position representation. Acting with the interaction potential operator on a two-particle position eigenstate gives the scalar interaction potential evaluated at the position eigenvalues times the associated eigenstate. Using this result, we end up with this expression for the matrix element. This is now just a scalar, so we can move it outside, and we end up with this new expression. This here is the scalar product between two tensor product states, and using the usual rules for tensor product states, it can be written as the scalar product of the states in space 1 multiplied by the product of the states in space 2. Bringing these results together, we end up with this expression for the matrix element. The basis is orthonormal, so this bracket is a Dirac delta function, and this bracket is also a Dirac delta function. So we end up with W of R3 R4 times the Dirac delta function of R1 minus R3 and the Dirac delta function R2 minus R4. Let's make some room, and let's copy down our latest expression for the matrix element. We can now go back to the full interaction potential operator W, which remember can be written as these four integrals over the matrix elements of this product of two creation and two annihilation field operators. Inserting this matrix element into the operator, we end up with this very long expression. And I can't really fit it into a single line, so I'm going over to a second line. We can now evaluate the integral over R3, and this Dirac delta function means that all R3 become R1. And we can also evaluate the integral over R4, and this Dirac delta function means that all R4 become R2. We end up with an integral over R1 and an integral over R2 of W of R1, R2 times this pair of creation operators and this pair of annihilation operators. And that's it. This is our interaction potential in terms of field operators. We can see that we no longer have 4 integrals over R1, R2, R3, and R4, but instead we only have 2 integrals over R1 and R2. So the interaction potential energy in terms of field operators is again somewhat simpler than the general expression for a two-body operator. To finish, we can now bring all our results together to write the full Hamiltonian for a system of n identical particles in terms of field operators. First, remember that the Hamiltonian H has a kinetic energy term T, an external potential energy term V, and a pairwise interaction term W. In terms of field operators, this is the kinetic energy term we've derived. This is the external potential energy term. And this is the interaction energy term. And this is it. This is our full Hamiltonian in terms of field operators. I can't emphasize enough how important this Hamiltonian is. For example, it allows us to describe the behavior of electrons in molecules and materials. In this case, the external potential here is the Coulomb potential arising from the positively charged atomic nuclei, and the interaction potential here is the Coulomb interaction between electrons. Such a Hamiltonian is at the foundation of chemistry and of condensed matter physics. Now that we've written the Hamiltonian in terms of quantum field operators, we're ready to study any system of identical quantum particles. As a next step, you can check out our video where we study the Heisenberg picture in second quantization, where we explore the time evolution of quantum field operators as driven by the Hamiltonian. I hope you liked the video, and please subscribe.